doctor in Department of Math. Now I'm just waiting for my higher studies, right? All right, so you can interrupt me at any time you want, whenever you have any questions or anything. Like, I just wanted to make it more like clear discussion rather than just I'm talking and you guys are listening, right? You can just stop me at any point, and when you have any questions or it's like any other sort of methods, you can just stop me, right? So we are just going to discuss some questions. I hope you guys already have the how are the questions, also like which are the areas that are going to be covered, right? So you are just going to have MCQ type questions, but so while doing approaching MCQs, you can just and you have only one correct answers on all among them. So you can definitely find the correct answer by eliminating the other answers as well. And like even the questions we are going to discuss today, they can be done like that. But like for in a point of view of to give you the clear idea of and concepts, we'll go through each and every answers as well for this training session. But keep in mind when you are doing it as a quiz or something, it's not recommended to go through like that, right? Okay, so and you can interrupt me at any time you want, and if you guys are not fluent in English, and if you wish to ask in other languages, you can ask. I mean, in other languages in sense Tamil or Sinhala, right? So you can interrupt me and ask on other languages as well, right? So let's begin with some questions, right? So I'll give you maybe few minutes for just to go through the question, or else like just to attempt it. Then we can discuss. Let's go like that, right? Or else like you wouldn't have time to think, as I think. So just take some time and try the first exercise. And if you have the answer, or else like if you wish to share something, or else like you may always unmute. Okay, unmute and talk. Or it's like if you are feeling awkward to unmute and talk, you can always send messages to the chat, right? Try the first question. And I forgot to mention, like, so as the committee for the quiz decided, your questions will be based on your first real analysis course. That means like, the elementary analysis uh, things like sequences, series, and like monotone convergence theorem, like intermediate value theorem, differentiability, and like those stuffs. Okay. Feel free to drop the answer on the chat if you find it out, or it's like, and you may also let me know if you wish to elaborate it, or it's like share your thoughts on the questions as well. So I haven't received any answers. So that just means like, do you guys need more time, or it's like Okay, maybe I could give you some hints if you guys are struggling. And uh, okay, I'm getting some answers now. Right, that's really awesome. Nice. Okay, that's awesome. Yeah, that's really nice. Yeah, you guys have the idea, right? So, would any of you mind to share it here, or just like shall I just explain?
By using the mean value theorem.
Exactly, right? So by using the mean value theorem. So mean value theorem is the key point here, right? So so the question asks what is the greatest possible value for f0, and it only says like the derivative is not getting lower than -1, right? So at the first glance, the question seems like okay at the point 3, the function value is 5, but they're asking the function value at the point 0, and they have only limited the derivative to be not going below -1, so it can go as much as we want to the above. So what would restrict it to go to so uh, so big a value? What would be restricting it to go to that value? But if you recognize it clearly, so whatever value it is going to get, it should eventually get back to 5 when the x value, when you are inputting 3, right? So when it is getting back to this value, that's where the mean value theorem is going to come to play, right? So when it's coming back to this value at 3, when it's coming back to 5, right? Uh, if your f0 is too big, it would eventually get the derivative at a point to be greater than sorry, less than -1, right? So that is where the mean value theorem is going to come to play. So let me briefly tell what mean value theorem is as well. So mean value theorem says like if you have an open interval, um, or as like if you have say A and B, and okay, something happened. Let's see. Okay, so if you have two values fa and fb, so you will always have, whatever the graph looks like, that's totally fine. You will always have a point where the gradient at that point should be equal to the gradient of the line connecting to those 2 points, right? So that is what the mean value theorem is all about, right? So if you write fb minus fa over b minus a, okay, so you would definitely have some point c in between a and b, right? Some point in between a and b, which at which if you take the derivative, that is going to be equal to that thing. That's what the mean value theorem says, right? So if this point is like is any value greater than 8, so I'm just assuming I'm just connecting it with a straight line, right? Say for example this place, if I connect it with a straight line with derivative of -1, then the value at this point is going to be, if this is 5, the value at this point is going to be 8, right? If it is a straight line with gradient -1. So it can be any other curves as well. But if it is any value greater than 8, right? If it is any value greater than 8, you may think like, okay, I might try to come without making the gradient less than -1, but how hard you try, you would eventually end up at a point with um, a gradient less than -1 because of the main value theorem, right? Because like if you, for any value here, say for example c, so any value here, c minus 5 divided by the 3 is going to be less than -1, right? So at a point in between this 0 and 3, you are going to have the derivative less than -1, which is going to be contradicting these things. So the greatest possible value that could occur is 8. So that is the idea, right? So you may just use intuition to get the answer. That's totally fine. Like, okay, so the derivative cannot go below -1. So the most uh, most optimal value to get the slope is at -1, and when you get -1, the value is 8, so 8 should be the answer. You can get it like that, but in order to argue it rigorously or else like prove it, mean value theorem is the key point. Okay. So is that question clear for everyone? That is what that question is about. Okay. So if you have any other problems with that question, you may ask. If not, you can give it a try for the exercise 2. You guys are familiar with series as well, right? Can someone confirm me? That was in the syllabus that was shared. You guys are you guys familiar with series and like tests? Someone was coming to say something, but I think I interrupted and chased him away. Are you guys familiar with series and the tests which are used to find the series are convergent or not? Yes. Oh no. If it is no, I can just briefly explain the tests and you can proceed. That's why I'm asking. If you guys are familiar, you can give it a try. Okay, shall we look together maybe? What about the first one? What do you think about the first one? Is there any tools you can use to determine whether that is convergent? Come on, guys, you can talk or like chat and like that's totally fine, right? Even if it is like if you feel like it's stupid answer, don't worry, right? That's there's no stupid answers.
Ratio test.
Yeah, you can go with ratio test. Would it be working here? I think it would, right? So what is the ratio test? So let me recall for those who uh, couldn't remember. So what is the ratio test? So if you have a series that is you want to determine whether that is convergent or not, what you do is like you just take the ratio of an plus 1 divided by an, and you will be taking the determinant and seeing it is less than 1, the series will than 1. My connection. Yeah. So if the limit is less than 1, series will be convergent, and if the limit is greater than 1, if it is equal to 1, you right with that test. That doesn't mean like the series would be divergent. You cannot determine with that test. Okay. So series will 1 divided by n. Uh, I think things would can get 1 at ratio test. I'm not sure. Let's give it a try. Or else like you can use to compare these series with something else. Like that would be an easier method on these circumstances. I mean, like you all the values of an is less than or equal to bn, and if the series bn converges, then if they are positive series, as like of course, like if the series bn is convergent, then the series an should be convergent. On the other hand, if series an is divergent, then the series bn should be divergent, right? So so that is a comparison test. So that would be more handy at this place, as I believe, because ratio test would give you like something like 3n plus 1 over n square plus 5 divided by 3n plus 1 plus 1 divided by n plus 1. So uh, it seems to me that when you take the limit as n goes to infinity, it's going to be just 1. I may be wrong. Uh, but comparison test would give you an easy approach. And you compare the series which would be converging, and then you can decide what would be happening. All you have to do is you have to find a series sequence which is greater than or equal to this one, or less than or equal to this one. I mean, like, if you want to show this series is convergent, you have to find something bigger than this one that is convergent, or else like you have to look for something smaller than this one that is convergent, so that is divergent. Then you can show this series is divergent, right? So you can always use the fact like 1 over n to the power n square is convergent, n cube is convergent, like n to the power p is convergent as long as p is greater than 1, and 1 over n is divergent. You can use that and bigger than, which is convergent, or else like try to create something smaller than that one, which is particularly the series would be converging, sorry, diverging. You guys get the idea, right? Even if the smallest one is divergent, this guy is bigger than that one, so it's going to definitely going to go to the infinity, blow to the infinity, right? So let me help you with something maybe. So you have 3n plus 1 divided by n square plus 5, right? So how can you make this bigger and try to, we are trying to get something like a constant over into the power p, okay? So how can you make this thing, if I'm planning to make this bigger, how can I make this thing bigger? Greater than or equal. So there are two things you can do to make a fraction bigger, right? Like you can make the part on the up bigger, or it's like part on the bottom smaller, right? As long as it's a positive quantity. So that's how you can make these things bigger, right? And if I want to get rid of these numbers and everything, I can, if I want to make this bigger, I can just, how can I remove this 1? I can just replace this 1 with, maybe, I can just replace this 1 with,
In
yeah, exactly. Really awesome, right? So you can just replace it with n and you'll be getting it bigger, right? And also to make this denominator smaller, the part on the bottom smaller, you can just remove certain parts which are positive, right? But be careful, don't make sure the part on the bottom would never get 0, okay? Then it would be totally undefined. So you can just remove this 5 on the bottom, right? So that way you will be getting like n square. But the problem is like you get something like, this is like 4 over n, and 4 over n is divergent, right? Series of 4 over n is divergent. So that doesn't give us a conclusion that this series would be divergent. Something bigger than that is divergent. That doesn't mean like this one is smaller one. Like you cannot say it's divergent. For example, if you take a series of summation of 0, that's going to be convergent. But like if you take the summation of like n, that is going to be divergent, and n is greater than 0. So you cannot argue like this series should be convergent, right? So if you are trying to show a series is convergent, you have to find a smaller series than that is convergent, right? If you're trying to show a series is divergent, you have to find a like if you are trying to show a series is divergent, you have to find a smaller series than that which is divergent. If you are trying to show a series is convergent, you have to find a series bigger than that is convergent, right? So so this is not going to help us. So can you guys try to make these things smaller and find something that is convergent over n square plus 5? Can you guys try to make these things smaller? Can you guys try to find something smaller than this one? You're going to do the same drill, but like in a different manner, right? Like if now you have to make the numerator small and the denominator bigger. So what can you do? We can remove this one, right? If we remove this one, that's going to be smaller, and like you can make this bottom part bigger, like or else like denominator bigger by like just making this 5, turning this 5 into something which would help us simplify the things. You can change this 5 into 5n square, right? Still, it's going to be getting smaller, like because like you are making the bottom part bigger. Like if you are dividing by a larger number, you are going to get a smaller fraction, right? So you can just replace 5 by 5n square, and then you will be having 3 over 6n, right? So as we have discussed earlier, as I have explained earlier, like the series of summation of 1 over n is divergent, right? So if the summation of 1 over n is divergent, then this is a constant time summation of 1 over n. So it's also going to be divergent, right? So that means this series is going to be divergent. Is it clear for everyone? So we found a guy smaller than this one, which is diverging. So obviously this series is also going to be diverging because it's a positive series. Is it clear for everyone? Yeah, that's nice. Um, consider it as P series with can we take 5 and instead and consider it? You mean like instead of 5n square, you are trying to take it as 5n and do some simplification. Is it so? I got a message from someone suggesting some other alternative. That's really awesome. You can always suggest, right? Is that what you were saying? Like instead of 3? Yes, like yeah, you can proceed in different methods. That's totally fine. Like I took it as 5n square because like that would make the simplifications much easier, right? Like that would make the things cancel off and like that would help us do the works easier. But if you take it as 5n, then it's going to be looking like 3n over n square plus 5n, and which you can't just directly cancel everything out. Like you will be left with 3 over n plus 5, and like then you have to do a little bit more work to show this is also diverging, right? Yeah, it is divergent, but you have to be a little bit careful, and like that's it, right? And if it is an MCQ case, like yeah, you can see, if you can see it directly, there's nothing to worry, right? But that's a good suggestion, right? Nice. Okay, so how about the second series? Am I going too slow, or like am I talking too fast? So like let's just let me know, right? So how about the second series? Is it convergent or divergent?
Divergent.
Divergent. Nice. How would you able to say that?
From the nth term divergence test.
Okay, so nth term divergence test. That means like if the AN sequence, the sequence is that the test what you were saying, or is like
Uh, yeah, check the limit as n approaches infinity.
yeah,
It's
that's
1.
Yeah, exactly, right. So that's a easy approach, right? If a series is convergent, then definitely the limit of an should be convergent, right? So and it should converge to zero, right? Exactly. That's really awesome, really smart, right? So the sequence an should converge to zero. That's only then the series would be converging to some value, right? Because it makes sense, right? Like if you are adding up some values and like eventually, even if you add infinitely many values, it's approaching some value. That means like eventually you should be adding smaller values, like which is approaching zero. Or as like if it is approaching some constant value, it's like you're adding that constant to the constant again and again, right? Like it's more or less like that in rough sense, but so it makes sense that if a series is convergent, definitely this part should be converging to zero. But keep in mind the converse, or it's like the reverse is not necessarily true, right? So because like an obvious counter example would be the series 10n diverging. Okay, so you can refer to the proof of series 10 why series 10n diverges on any analysis textbooks like Rudin's or it's like Tau. And the series 10n, even though the 10n converges to zero, the series 10n diverges, right? So if the if the series is convergent, the part inside should go to zero. But like if the part inside is going to zero, you cannot say the series is convergent, right? So it's more like if you see something, if you see a crow, it's black. But like if you see something black, you cannot say it's a crow, right? Okay. So from the contrapositive of the second statement, if the series is convergent, then the thing inside should converge to zero. So the contrapositive of that, if convergent implies an is equal, an should go to zero. So the contrapositive of that, if an does not go to zero, if logically if p implies q, you can always take the contrapositive. If negation of q should implies the negation of p. Okay, if an does not, an goes to zero. Yes, is it some doubt? I cannot hear you. I hope it's an accidental one, right? So if an does not go to zero, then the series is not convergent, right? So that is the contrapositive, right? Okay. Uh, that means like if it is crow, it is black. If it is not black, it is not a crow, right? So if P implies Q, you always have like not Q implies not P, right? Okay, so using that, you can always have this series should be diverging, right? So how about the third one? Third one looks okay. Uh, Yes, so it there is like one that's a really interesting question. Like one of you asking like how can we determine whether series is convergent or divergent on beforehand? Like how can we surely know which test to apply? But the problem is like we don't have certain rules. Like okay, this test would definitely work and all. Like it's like mostly like trial and errors. Like but like with experience, you will be able to understand okay like these sort of tests won't be working at these points and like that, right? And if some test is failing, like then you will be eventually moving on to the other tests. So um it's just with experience. Like you cannot definitely say whether that's a series is convergent or divergent at first glance. Like you just try um at some extents, like okay if, seeing this one, it makes it like it looks like it's something related to one no n, right? Because like and the upper part is dominated by n and the lower part is dominated by n square. So if the things cancel out, you are getting something similar to one no n, and one no n is divergent. So I expect this series to be divergent. So I'll be starting to make this series smaller, sequence smaller than this one, and try to find something that is diverging. So that's how I usually approach. But it depends, right? So with time you'll be and practice you'll be recognizing. Okay, don't need to worry if you didn't get it at the first glance. Okay. Uh, if the limit of the nth term is 0, isn't the test inconclusive? You mean like this one, like the series? Yeah, like that's what I'm saying. Like if the limit, Wait, um, wait, isn't that what I was mentioning? Like if the series is convergent, then definitely the part inside should go to 0. Like if it is not going to 0, then you cannot say the series is convergent, right? In the other sense, like what as that particular student asking, like if you have the sequence is going to 0, the sequence inside the series is going to 0, you cannot say anything about the series whether it's converging or not, right? Okay, that's what I was telling about the converse of this statement. You don't have the converse of this, right? You have certain series which for which definitely an is convergent and the series is convergent, and you have certain series where the an is converging to 0, but like the series is not converging, right? Okay, so just because the sequence inside is going to 0, you cannot say the series is convergent. But if the series is convergent, you can definitely say the sequence inside is going to 0. That's what I was trying to say. Okay, is that clear to everyone? Okay, how about the third one? Third one seems to be a little bit tricky, but yeah, since the time is also running, yeah. You can try to go with ratio test as this would be an answer for the person who asked earlier. Like you can try to go with ratio test or something, but it feels like it's going to make things more complicated, right? Like you already you have sine 1 over n and cos 1 over n, like, and if you go with ratio test, you are going to have sine 1 over n over sine 1 over n plus 1, and like cos 1 over n plus 1 over cos 1 over n, and like the things are going to get more complicated, right? So would there be another approach? Maybe can go with the same thing I was mentioning earlier, maybe like but comparison test, but how can we, and you can see like this is the most annoying part, right? So if you have a way to get rid of that annoying part, we have the job done. So can you guys see a method to make this like greater than c over n square? Then I have everything I want, right? For some constant c, then I have everything I needed. Then I can see like series of n square. 1 over n square is convergent. That means like c of n square is convergent. That means like series of these things should be convergent, right? Keep in mind this only works for positive series, because like obviously um like to specifically for the other hand, like if a sequence greater than an, if bn is greater than an and like bn is divergent, then to say an is divergent, both of them should be positive, right? Or else like you can definitely say take like 1 over n square is greater than -1 for all n, and like this one is the series of 1 over n square is convergent, so series of -1 is convergent, and you will be ending up at some weird place, right? Any idea to make this constant, or it's like bound that quantity by a constant maybe? So what is sine 1 ON or tan 1, cos 1 ON? It's going to be tan 1 ON, right? And the tan graph would be looking something like this, right? What are the values I'm going to get when I plug in each natural numbers? If I plug in 1, I'm going to get tan 1, right? And if I plug in 2, I'm going to get tan half and all. So are we getting somewhere? Are you guys seeing something? Eventually, when I plug in bigger and bigger n values, I'm heading towards 0. So for all n, can I find a fixed value which is greater than tan 1 ON? Yeah, I was, yeah, wait. We are trying to make this series convergent, right? Yeah. I was messing up. Sorry. I'm trying to find some series which is greater than this one, which is convergent, right? Yeah. Sorry about that confusion. So can you find a C for which you can always make tan 1 ON less than that C, a constant for all natural numbers? Then we can just replace that C, and like this new sequence is would be always greater than that thing, right? And series of C over n square is convergent. Can you find a C? As you guys see, like when n increases, these terms are going closer and closer to 0, right? So that means like tan 1 is the biggest value among all of these things, right? So tan 1 over n should be less than or equal to tan 1, right? For all in the natural number. So we can just replace this tan 1 over n by just tan 1. Then you have the answer, right? So that means like you can just replace this one by say C, the constant C I'm taking is like tan 1 over n. Tan 1, right? Tan 1. So I have a sequence which is bigger than that one. And the series of that thing is convergent. So that means like series of sine 1 over n over c square cos 1 over n. So sine 1 over n over n square cos 1 over n should be convergent. Right? Is it clear? Does that make sense? I'm not saying like it always works like you can bound this part, but like here it was much easier because like we were able to find about. Is it clear for everyone? Whatever the value you put in for the sine 1 over n and cos 1 over n, that means like whatever the value you put in for the tan 1 over n, you can see from the tan graph, right? Tan goes to infinity as at pi by 2, right? And it increases. So when you put 1, you're going to get tan 1, a value somewhere. We don't know. And when you're going to put 2, you're going to get tan half, tan 1 over 3, and something like that, right? So the values are eventually going to go lower, get lower. So the tan 1 is the biggest value among all of those things, right? So that is what we were looking at, right? Yeah, sorry. So how about the fourth and fifth one? Yeah, we are spending a lot of time on these things. Let's go through them quickly. So so we have found this one to be okay. So is we found this one to be convergent, right? Right. So this the third one to be convergent, and um, we found it to be convergent, right? We made it to one over n square greater than that thing. Yeah. So yeah, we made it to be convergent, and the second one was diverging, and first one was diverging. And yeah, I think there's going to be two answers for this question. Yeah. So the fourth one, maybe limit comparison test with 1 over n squared. Uh, can we apply the limit comparison test with 1 over n squared? You mean like um, trying to yeah, that's kind of the same idea I'm using here, right? What were you referring to? Can you, if you don't mind? We are trying to compare these things with c over n square, right? For some constant c for
By dividing by 1 over n squared, taking Vn to be 1 over n squared,
okay,
because 1 over n squared is convergent and the limit approaches 0,
yeah.
uh, then Un should also be convergent, right?
Yeah, yeah, you mean like just considering this sequence and then dividing it by 1 over n square and seeing the limit, right?
Yeah.
Yeah, yeah. Actually, the both of these this comparison test and this thing, both of them kind of says the same thing, right? Eventually, the proof also goes kind of similar. So that's also an acceptable approach, right? Okay, so shall we look into the fourth and fifth one really quick? Okay, so or else like we'll be just discussing series. So what about the fourth one? So fourth one, yeah, you guys can give it a try with the comparison or as ratio test and everything, but I'll not spoil for you. You can just give it a try with that as well. And eventually, mostly you would get stuck at some point because like you'll be having log n or log n plus one, and like it gets worse. But so um, if you guys haven't heard about it, I'm not sure whether have you guys heard about Cauchy condensation test? If not, maybe you can refer to this test and see whether this series is convergent, right? Like I'm just going a little bit faster and skipping these things so we can just other questions discuss the other questions as well. This is a kind of an easy idea. Like the idea is like if you have two series as like an, if you have a series an, the series an is convergent if and only if the series 2 2 to the power n a 2 to the power n is convergent, right? You are just replacing n with 2 to the n and like putting a 2 to the n in front. And if this series is convergent, then this is series is convergent, and if this is divergent and this is divergent, right? So just give it a look for the Cauchy condensation test, and like you can always try to put ratio test as well and try to approach this as well, right? It might be a little bit tricky, so I'm just giving it for you to try, just as the mathematics book authors exercise left as an exercise. Okay, so just to go through this as well quickly. So what is going to be the an plus 1 minus an here? UNC is equal to 0 is not going to be a problem here. Like yeah, but what is going to be an plus 1 minus an here? Just going to be a n plus 1 is c plus n plus 1, and an is going to be just c plus n. And if you subtract, you are just going to get 1, right? So this is going to be just representing 1, a constant. And as you guys indicated earlier, like the part inside is not going to 0, so that means the series is not going to converge, right? So that is also something easier to recognize. Okay, so for this one, if you just use the Cauchy condensation test, it's going to be coming easier. But without that, there might be approaches like you can use integral test and things like that. But just give it a try. Okay, like try to go with the ratio test as well and play with it. Like and it might get somewhere. Okay. So considering the time constraint, should we go to yeah? Let's discuss the third one as well. Yeah, let's discuss the third one, and then think about what's the next. Okay, so okay, how about the third one? Oops. So you have a function and two binary operations, and it just asks like uh, whether the function is commutative and like is satisfied the distributive law and like right distributive law and all. Can I have what opinion? Extremely sorry about that. Yeah. So can you guys give it a try? So for you can give it a try while I explain what is commutative and everything for those who couldn't remember. So commutative, you can just remember it using the idea of communism as well. Communism means like everyone is equal, right? No one is prioritized to come on first. You can just change and like nothing is going to change. So an operation is commutative if you have a plus b is equal to b plus a, right? Not plus the operation, right? If you can change the order and it preserves, then we say that operation is commutative. So obviously the addition, multiplication are commutative, but division, no, right? You cannot say like 5 divided by 2 is equal to 2 divided by 5. That's totally wrong, right? So certain operations are commutative and certain are not. And here they are asking like, does the composition operation a commutative? Is the composition operation a commutative operation? That means like, do you have f composed with g, x is same as g composed with f, x for every functions f and g from real to real? Do you have that thing? If you guys think it is yes, actually the correct approach is to prove it rigorously. And if you guys think it is no, no need to worry. Just you have to just find two random things, two random functions, and show them. Oh, okay, for this function is false, so the statement is false. That's it. First of all, do you guys think it is commutative or not? Okay, I'm getting some answers. Yes. What about the others? It is not, right? Very good, right? It is not, right? Like you can just take gx to be maybe um yeah, you can even take uh some any continuous function, maybe like fx to be sine x and gx to be x square. Then f compose g would be uh, fx gx to be x square. Then f compose g is, that means like this means you are putting gx inside the function fx, right? So that means you are having sine of x square. Does it necessarily equal to the other way? G O F means like g of f of x. That means like x square of sine x. That means like sine square x. These two are not equal, right? So it's obviously not commutative. So how about the distributive law? Okay, I'm getting some answers. That's nice. Is it distributive? I'm getting some mixed answers. You may think with some example like just gx equal to x and hx equal to x and maybe fx equal to sine x. Or else like fx equal to x square, maybe. Anything would work. This side means like f of gx plus hx. That means like, right, f of gx plus hx, that means like sine of x plus x, right? And the other side, we'll be having like sine of x plus sine of x. Or as the other example, x square, you have here, you have like 2x, x square wouldn't work maybe, yeah. So it's there for you to find, right? Like if you couldn't find a counterexample, that doesn't mean like the statement is true. Then you have to try to prove it. Okay. So so that is not distributive, left distributive, right? You cannot say sine x plus x. Sine 2x is equal to sine x plus sine x, right? Okay. So that I hope that is clear. And you can, yeah, the x square would also work, right? In this side, you have x plus x square, right? That means 2x square, that's 4x square. And on this side, you have x square, that means 2x square, right? So it's obviously not left distributive. So can you guys think of the third one? Is it right distributive? Okay, I'm getting a counter example, but let's see. Let's see that counter example whether that works. Okay, right. I got a counter example saying like f to be x square and g to be cos x and h to be sine x. Let's see whether that works, right? So the right distributive law says like, what do we mean by g plus h f composed with f? So g plus h, if we take g plus h x as a function, this means this just means like gx plus hx for each x, right? That's how what we mean by g plus h x. That's how we define addition of two functions, right? So so would this counterexample work in that sense? Shall we look? Cos plus sine x. So f to be on this sense like composed with fx we have. So g plus h fx. So if we have g plus h fx, then it's going to be something like this, right? Cos plus sine of fx means like x square, means by the definition it's just going to be cos x square plus sine x square, right? So it's going to satisfy, right? So you can see, like, since we define the addition of functions by this manner, you can write a complete proof as well, right? So so g of x plus f of x, h of x is going to be like this. So that means like g of g plus h of f of x is going to be just, by the definition, it's going to be just g of f of x plus h of f of x, right? All we have to have is like the function should be defined properly to define the composition and everything. As long as we have that thing, assuming we have that thing, so it's just going to be g of hx plus g of fx. That means like this is going to be g o f of x plus h o f of x. So this third statement is going to be true. Okay, the other two are false. Is it clear for the person who suggested the counter as well? And for this is how we define the addition of two functions. Okay, in case if you have forgot. Is it clear, guys? That's nice. Okay, so let's quickly move to the quantifiers and everything, right? A question on quantifiers. So these things, even the third question and fourth question, they are more towards more than analysis. They are more towards the foundations of mathematics, right? Like the concepts you will be using in the mathematics and everywhere. So, anyways, I included them in analysis related questions because, like, you would see, like, on the epsilon definitions and everything, like, you should be familiar with quantifiers, right? Okay, so what about these statements? Like, and is there anyone who wants me to explain these things briefly before we proceed to this questions, or else, like, would you guys want to try? Okay, I'm getting something. Yeah, sure. So I'll briefly explain about these quantifiers and everything, right? So that might be confusing if you guys are not so much familiar with it, right? So first one is like we use this symbol. That means like there exist. So if you are talking about a set, if you are talking a statement about the elements in the set, so this means there exist. So that means like there x. If you say like there exist x belongs to A and a statement px, that means like you're saying you can find an element from that set, making that statement true, right? So that means like there exists an element from the integers on which x is equal to, if I define that statement, maybe uh, x is greater than 3. Okay, so you can find an integer which is greater than 3. You can obviously take 4, you can take 5, you can take 10. Like there are many. But all you want for this statement to be true is like you should be able to find, or it's like you should be able to state there should be an element, right? Even sometimes you won't be able to explicitly say like there's this that element, but as long as you can guarantee there is an element, that statement is true. Okay, there exist existential quantifier, right? So so uh yeah, and the other quantifier we would be mainly dealing with is universal quantifier for all x in the A. What does this means is like this means like the given statement is true for all the elements in the set. So if I define the same statement for all x in the A, x is greater than 3, then this statement is false. Like because like I can this says like whatever the x you pick, you can take any x from the set, and if you take that x, it's going to be greater than 3. But I can pick integer -1, right? And I can pick the integer 0, right? Which is not greater than 3. So this is what the universal quantifier is, right? This says like all the elements in the set are satisfying, and this says like there is a particular element, right? So the each of them is like the negation of others, right? Like if you are like negating the statement as well, like that means like if you say this statement is false, if you say like if I'm saying I'm just coming and saying like okay, in my class all the students got scored above 70, and if you want to prove what I said is false, then should all the students score below 70? No, right? Like to prove what I said was wrong, you just need one student, right? So the negation of there exists x in A px is nothing but for all x in the A, not px. Okay? So the negation would just change the quantifiers the other way around. So if I say there is one student who passed the exam, and if I said is false, then that means like all the students didn't pass the exam, right? So that's how we negate. And the other way around is true as well. Like if you take for all x, if you have a statement and if you negate it, it's going to be changing the other way, right? So that are the basic things. And then we'll be coming up with mixing up the quantifiers, right? We'll be mixing up quantifiers, and we'll be stating like for all x there exist y is blah 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 blah. So what does that things means? Like meanwhile others can try the fifth question. If you guys feel like this is just boring revision, you guys can try the next one as well. Okay, so I'll just keep it on a side. So that is what the quantifiers is about. And like, what about the statements like there exists x for all y, some statement pxy, something like this. This means this and the other thing are totally different, right? This one and this one looks similar, but they are totally different things. Okay, so let me mark it with B maybe. Yeah, let's consider two sets, right? That's much general. Yeah. So for all y in B, there exists x in A such that pxy. These two things are totally different, right? So you'll be reading from the left to right, just as we read normally. So this says there is an x. You can give me an x for which whatever the y you pick from the set B, the statement is going to be true. Right? So for example, you have two sets, A and B. Say for example, A is the set of integers and B is a set of A is a set of integers and B is a set of positive integers. The first statement says like you can, like if I take pxy to be maybe like x is less than y. Okay, less than or equal to y. The first statement says like there's one particular element from this set A. You can find an element. It doesn't have to be unique. You can find an element from the set A for which that element is less than or equal to any element you are going to pick from the set B. So you have 0, right? You have 0 from the set A, which is less than or equal to any element you are going to pick from the B. So you cannot change this one after you picked it, okay? In this order, there exists x belongs to A for all y belongs to B. That means like you have already taken x in the hand. You cannot drop it. The second one says, for all y, there exists x. That means like, if you give me a y, for that y, I can select an x. If you give me another y, for that y, I can select another x. Okay, or else I can use the same x. That's totally fine. The second one, the x can be changing with the y. Okay. So if I define this a to be the integers and b to be the integers, and if I say like this statement to be x is greater than y, maybe x is greater than y, yeah, or else like just let's keep it as positive integers. So this statement would be still true, right? For all y, you can stay like 10 trillion. You can just give me 10 trillion. I can find an x, 10 trillion and 1, or it's like 20 trillion, which is greater than that thing, right? But I don't have a unique one, which is working for everything. Okay. In that case, like this statement would be false. If I write like there exists x belongs to A for all y in the B, x is greater than y, this statement is false. Like there's not one unique element which works for all, right? If it makes sense, does it make sense? That's all about these quantifiers and like mixing quantifiers. Right. So so what would be happening for this one? So here we have a similar statement, right? X is less than or equal to y, and we are defining it on a set which is proper subset, which is a subset of integers cross integers. So those who have tried, what do you think the answer is? Or it's like let's do it together, right? So what would be the first statement? The first statement say like there is an x for all y. We don't know about this set A, right? It could be any set, but if this statement is true, can you definitely say this statement should be true? That's what we are looking for. Okay, that's what an implication is all about, right? P implies Q means like if P is Q true, Q should be definitely true. There cannot be a counter example where you can make P true and Q false, right? So How is this going to work? Like there exists an x for all y, the statement is true. That means like you can find a unique x, whatever the y you are going to pick from the second set, from the integers. I mean like the a, you have to take whatever the y you are going to pick, the statement is true. So can you say, that means like whatever the y you are going to pick, your x is going to be smaller than that. Can you say for every y you can pick an x? If there is an x for which all the y's are satisfying this certain condition, can you say for each y, whatever the y you are giving, I can find an x? The first one says there's one unique x, and for I have taken an x, and this x is like if you give me any y, I have already taken an x on my hand, and if you give me any y, this x would be working, right? I'm just going to drop this x again, right? Now the second statement is saying like whatever the y you are giving, can I find an x here which is satisfying that thing? Let me see. Yes, right? I can just select that same x again and again. Is it clear? So for example, like you cannot decide with just one example, right? But say for example, this a is the set of all the positive integers. Positive integers. That means like the first element is also from positive integer, second element is also from positive integer. So for you have an x, you have one which is less than or equal to whatever the integer you are, positive integer you are taking, right? Now, can you find uh, if I give you an integer, positive integer, can you find a positive integer smaller than that one, smaller than or equal to that one? If I give you, if you give me 10,000, can I pick a positive integer smaller than that or equal to that one? I can pick 9,000, and I can pick one as well, right? Is it clear? This one was working for all the elements in a set. So whatever the element you are giving, there can be a lot of elements satisfying the statement, but like I can always repeatedly take that one again and again, right? So from that, the first statement should be true. Okay. I feel like I'm speaking fast, or it's like I'm going faster. Usually I don't do like that. If you guys want me to tell things again or it's like clear things again, you can ask, right? I just wanted to make sure it shouldn't be boring, and I was speeding up. Maybe I sped up so too much. So what about the second one? If for all the elements in the set, you can find an x, can you say there's one x which would be working for all elements? For all elements, you can find a unique x. Sorry, for all elements, you can find an x which is satisfying. Can you say one x would be working for? No, right? That's it. You cannot say one x would be working for all y. A critical example would be if you take a to be integer cross integer, this statement is true, right? If you take a to be equal to z cross z, that means the right hand side says for whatever the y you are picking, like you can pick 100. Okay, can you find an x smaller than that one? 99. If you pick minus 10,000, can you pick a x smaller than that one? Yes, minus 10,001, right? What is like minus 10 billion? You can find a lot of, right? That's what this right hand side statement says. Like for each y, you can find an x. But what about the left hand side statement says? Left hand side says like there's one unique x which is less than all the y. Is it true? On the integers cross integers, can you find a smallest element? No, right? Obviously, x minus 1 is going to be smaller than this one, and x minus 1 is going to be an integer, right? Can you say x is smaller than all the integers? Can you find an x which is smaller than all the integers? No, right? That is why this reverse simplification does not works. Okay. So what about the last one? The a is an integer cross integer. Yeah, that's a thing we have already discussed, right? Like if a is positive integers, then you have 1, which is less than or equal to pi for all y, right? So you have there exists an x for all y that exists more than that thing. Okay. So this is all about the quantifiers, right? Quantifiers and quantifiers related questions, and you might need these things when you guys are dealing with definitions of continuity, limit, and like you're trying to prove certain things. You have to have a clear idea on. You won't be needing to prove on obviously for this quiz, but like to see the elegance and like beauty of mathematics. If you're trying to prove some things and results, you have to have a clear idea on these quantifiers, right? Okay, so we can discuss fifth one, but like considering the time, shall we discuss one other question? Maybe like yeah, fifth one is an interesting one, but like shall we focus on maybe yeah, shall we try the sixth one maybe? Let's try the sixth one. That's kind of more interesting. And yeah, obviously you can think of this question with what happens if it is instead of z cross z, if it is r real numbers cross r, what would happen? Try to think about it, right? Or it's like r plus cross r plus. Try to think about what would happen. Specifically for the last statement, if it is r plus cross r plus, what would happen? You can think about it, right? Okay, how about the sixth one? Shall we give it a try for the sixth one? Others as well, like others also respond, right? Like if you guys feel like I'm speaking fast or it's like things are not clear, just ask me. Like don't need to get afraid of, right? I'm totally fine with explaining. And like if you guys, I should have asked that question earlier. Like I was asking, like you can ask questions in Tamil or Sinhala as well. And or else, like if you guys want a specific part to explain on Sinhala or Tamil, like you can ask me, right? I can repeat it. So sixth one, that looks weird with a lot of supremum and stuffs, but okay, let's do it together, right? Like, what about the first statement? Can you say the supremum should exist? Supremum of all the fx values should exist on that set. Exist in real number. Okay, I'm getting some answers. That's really nice. I think they are recording. Someone is asking about the recording. I think they are recording. You can ask from the society members, maybe. Ah, yes, yes. Sorry, I was just seeing this message, and you guys, some of you guys, I should have shared this question maybe earlier. Yeah, I was thinking about it. So I'll just share the PDF with you guys now. So you can think about it. Meanwhile, you can give it a try, right? I shared it with Ketmger. And recording, I'm not sure. You should ask the society members, right? Okay, so what about the first one? Do you believe the supremum exists in R for the if? So what is a supremum? Supremum is the least upper bound, right? Like, so if you have a set, right, and if you just order all the values, so you have a lot of upper bounds for that set. So for example, if you have set like x is less than 5, all the numbers less than 5, real numbers. So you have a lot of upper bound for that. Like all the elements in the set are less than 10. All the elements in the set are less than 100. So all the elements in the set are less than 6. At the same time, all the elements in the set are less than or equal to 5 as well, right? Yeah, I'm getting some lines out of nowhere. Sorry. So all the elements in the set are less than or equal to 5 as well, right? So 5 is the least upper bound for that set, right? So you have a lot of upper bound. What is the smallest upper bound you can have? So for x is less than 5, the smallest upper bound you can have is 5, okay? So the smallest upper bound you can have is 5, okay? Oops, there's some bug. Oh, like this. Okay, so similarly, if you have a function fx, oh, why is this happening? Just give me a minute. Just give me a minute. Okay. So meanwhile it's loading, I'll explain. So yeah. Okay, so for a function, if you at the same time for a function, if you are talking about the supremum of the all the values of the function, so that's what this exercise 6 is about, right? So if you have a function, and yeah, now it's okay. Okay, right. So now if you have a function and that is defined from some a to b, and the supremum of the function's value maybe like would be the greatest value it is attaining, or it's like seems to be attaining as long as the function is bounded, right? So if it's an unbounded set, you don't have a supremum for that, right? Because like it's not bounded. Like we define supremum to be the least upper bound. So if you don't have any upper bound, so there cannot be any least upper bound, right? Specifically in real numbers. So if you have the set of natural numbers is not bounded above. Like set of natural numbers, you cannot find an element which is greater than all the natural numbers, right? So if you cannot find a number which is greater than all natural numbers, then the set of natural numbers is not boundable. So that means like set of natural numbers does not have a supremum in the real number, right? අප බවුන්ඩ් එකක් තිප්පනනේ අපිට කියන්න පුළුවන් පොඩිම අප බවුන්ඩ් එකක් කියලා. අප බවුන්ඩ් இருந்தா தான சொல்லலாம். சின்ன உள்ளதுல சின்ன අප බවුන්ඩ්, right? So in the case of unbounded sets, you don't have a supremum, right? Infimum is the same idea. Like you have a lot of lower bounds for bounded below sets, and we are looking for the greatest lower bound. Like we are trying to go as much as closer from below, right? That's what infimum is all about, okay? And uh, And so do we have a supremum for all the functions defined from A to B? Can you guys give me a counter example which it violates? If I don't have to have a supremum, function should go to infinite, right? Like it is not restricting the function to be continuous. So if the function is going like this, and at this point it is taking some value 0, and again the function is going like something like this, maybe. So this function fx values don't have a supremum. Okay, fx values don't have a supremum. Fx equal to x squared defined on a to b to r wouldn't would have a supremum, right? Someone was suggesting fx equal to x squared, but if you take fx equal to x squared and if you define it from a to b interval, it would have a supremum. Specifically, the supremum would be attained as long as a and b are positive, or it's like b is positive, the supremum would be attained at b, and it would be just b square, right? Is it clear? We are defining the function just from a to b. We don't care about what's happening at this side. Yes, something like 1 over x would work. Exactly, right? So 1 over x would work. And if you take a to be like something like, but again, you should be a little bit careful, right? Because like if you define f to be from a to b, a comma b to r, whatever the value you put inside this, whatever the value from the a b closed interval, if you take that value and like put inside the function, you should get an output. So if you define the function to be 1 over x, what's the domain you are defining? You cannot define it on open interval 1, 0, comma 1, right? So you can define it on closed interval 0, comma 1, but 1 over 0 is not defined. So you can use some piecewise functions like maybe like 1 over x if x is not equal to 0, and you can put another value like 5 if x is equal to 0, right? So this would work. This would be a function which is like for which supremum of f of x does not exist. Okay. So have you guys familiar with extreme value theorem, boundedness theorem? Yeah, the basic idea is like if this f is given to be continuous, right? If the f is given to be continuous, then you would definitely have the supremum on if for a function defined from closed interval to r. Then you would have definitely have that function is bounded, right? So that is a special sort of result. If you have a continuous function from a closed interval a to b, that function should definitely attain maximum at a point. That's what we call the supremum. If yeah, if the maximum is attained, then the maximum should be supremum. You can even prove that thing. And it would attain a minimum at a point, and definitely the function would be bounded, right? So that is, you have that result for continuous function defined from a closed and bounded interval into R. Okay, you don't have, if the function is not continuous, or it's like if the function is not defined on a closed and bounded interval, you don't have that result. So as some of you earlier suggested, the function is defined on 1 over like 1 over x, like on an open interval 0, comma 1. Obviously, it's not going to be bounded, right? But if you try to define a continuous function, if you try like in loose sense, but it's not the perfect way to define it. But like if you try to draw from a to b without lifting a pen, you cannot just go to infinity at a point and like come back, right? But it's not the way of defining it properly. Okay. Yeah. So that results are there. Okay. Extreme value theorems. Okay. So how about the second one? If the supremum does not exist, f is not differentiable for some c in the closed interval a b. if the supremum does not exist, that means the function is blowing up to infinity, right? Because it's a non-empty set. Any bounded set should have a supremum. That's on real numbers. That's how we define the real numbers. We were lacking of some certain elements which are supremum for bounded sets, and we put those elements inside, and that's how we define the real numbers. So for real numbers, any bounded set should have a supremum, right? If you bound it, there's a value which is like least upper bound. Like you cannot go below. If you go below, you are going to miss an element. If you go above, there's a upper bound lower than that, right? So there should be a least upper bound for any bounded set in R. And if the supremum does not exist in R, that means like it is not bounded, right? So just using that result I was mentioning right now, do you guys see anything? Maybe you can use the contrapositive as well I was mentioning earlier. If you have P implies Q, then you definitely have not Q implies not P, okay? If you have the supremum does not exist in R, then F is not differentiable at some point. That's what that statement says. There should be a correction on this fourth one. Just make that correction. This should be G, okay? If supremum does not exist in R, if function is differentiable, can you say anything about the continuity? All the differentiable functions should be? If a function is differentiable, then it should be definitely continuous, okay? But not the reverse. For example, mod of x function is continuous, but it is not differentiable. Okay? If a function is differentiable, it is continuous. You cannot say continuous function is different. All the continuous functions are different. But you can try to play with this one and the contrapositive. So if a function is differentiable, then it is continuous. And if you have the contrapositive says like if a function is not continuous, then it shouldn't be differentiable. Right? Okay. If a function is not continuous, it shouldn't be differentiable. Or else like let's just go with the contradiction and try to argue what happens for this one. Okay. So let's just go with the flow. Okay. So let's see. Let's say fx is supremum of fx does not exist. That means like f is not bounded, unbounded, as I was explaining now, right? So if supremum does not exist, as I was explaining, on real numbers, all the bounded set has supremum. So if it doesn't have a supremum, it's going to infinity. It's blowing up to infinity, okay? So if the supremum does not exist, then it's blowing up to infinity. It is unbounded. And can we have f is not differentiable at a point? It is going to infinity, as I was explaining earlier, on closed and bounded intervals, the function should be definitely a continuous function should be definitely bounded, right? So if it is not bounded, it cannot be continuous, right? So I'm going with the flow. I'll write it clearly here, right? If a function is not bounded, on a closed and bounded interval a comma b, then the function is not continuous, right? This is the contrapositive of the theorem I was telling earlier. On closed and bounded interval, all the continuous functions are bounded. That means like if it is not bounded, it is not continuous. So if it is not continuous, as I was explaining earlier, it cannot be differentiable. It is not differentiable, right? So that means like any differentiable function is continuous. So if it is not continuous, it is not differentiable, right? Any crow is black. So if you find something that is not black, it's not a crow. Okay, so we are just going with that flow. So we said like, okay, so if the supremum does not exist, then we said it is not bounded, right? So that is the proof, right? The supremum does not exist. It is not bounded. Therefore, it is on a closed and bounded interval. So on a closed and bounded interval, if it is not bounded, then that means like it is not continuous. If it is not continuous, it cannot be differentiable, right? So that means the second statement should be true. I understand that has a lot of prerequisite knowledge or like theories. If you haven't heard of, like, maybe you guys get confused, like don't worry about it much. Like you will be, when you try to digest it slowly, you may try to get it right. Okay. So shall we look at the third and fourth and fifth statements just for this question, and then we'll wind up. Okay. So what about the third statement? M is the supremum of all the elements fx exist. If supremum exists in R, can you say there's a particular value for which the supremum is attained? If a function is having a supremum on some, if you have a supremum for a function f defined from A to B, can you say on a particular value that supremum is attained? So you can just define a function like this, okay? Now the function's supremum is this value. Say for example 5. Function supremum is 5, but it is not attained at a point. Okay? Supremum is not attained at any point. Okay, is it clear? So if I define a function like fx is equal to x, maybe some easier way, fx is equal to x from 0 to half, and from half to 1, if I define it, if like x for x is in between 0 and half, and if I define it like -1 for x is in between half and 1. So for this function, the supremum would be half, and it is not attained at any point. If half is not half, if half is -1, right? The supremum is not attained at any point. Okay, so therefore this statement would be false. But as I was explaining earlier, if you have the function to be continuous on closed and bounded interval, there should be definitely a point where the supremum is attained, right? You can just try. I mean, like, you can try to prove the rigorous proof as well. But like, if you want to get the intuition, you can just try to draw a continuous function from A to B. Continuous function. You should start here and should end somewhere here. Continuous function. You shouldn't, like, in loose sense, you shouldn't lift your pen, and it's something like this, ending up something like this. You cannot do that, right? You will be definitely having a maximum and a minimum. Whatever the job you do, like, you will be having a maximum at a particular point, right? And the fourth one, maybe I'll just leave it for you to think. Okay, if you have two functions, and if you have two functions and both of their supremums are existing, can you say the sum of those functions, f plus g's supremum, should be equal to the individual supremums? That means, like, say for example, you have fx equal to x square and fx equal to 1, gx equal to 1. The supremum at all the points of this one is 1, and the supremum of fx equal to x square defined from maybe 0 to 1 interval is like, that's also 1. The supremum of the addition function is going to be, the addition function is x square plus 1, right? X square plus 1. The supremum of the addition function is going to be 2. It seems true for the example I took. Can you find a counter example for this, by this, where this goes wrong? Actually, this statement is false, and think about, you can find a counter example where that goes wrong. Okay. And the fifth one, it questions the theorem I was telling earlier. If f is continuous on each of these closed and bounded intervals. Okay. So in order to define something like this, I should have mentioned earlier, like b minus a should be greater than 2, right? Or it's like it doesn't make sense. B minus a is greater than 1 would be sufficient. Yeah, but like let's just say b minus a is greater than 2. Okay, or it's like the interval a minus 1 and b minus 1 wouldn't make sense, right? So what does this says is like, if you take this last statement, if you take f restricted to the f function on a plus 1 over n and b minus 1 over n on this interval, the f function is continuous. That means like a plus 1, b minus 1 function is continuous. Similarly, a plus half, b minus half function is continuous. A minus 1, a plus 1 over 3, b minus 1 over 3 function is continuous. If you have that function is continuous like on each of these restricted intervals for all n, can you say the supremum and yeah, continuous and the supremum is existing, right? So as I was telling earlier, if it is continuous on closed and bounded interval, supremum should be existing. So even without this, it works. Can you say the supremum from A to B should exist? On each of these intervals, you have a supremum. Okay, this one is the biggest one. This one is the biggest one. Can you say there should be a supremum from the A to B interval as well? I can see like the count dramatically dropped. Maybe like there was so much maths, so much theory put together on the same day. I get it. So we'll just wind up with this one and maybe continue on another day. But like, what do you think for this last one, fifth question? If f is continuous on each of the closed and bounded interval a plus 1 and b minus 1 can you say f should be supremum of a to b fx exist? So there should be a easier counterexample, like if you take like maybe even if the function is continuous for each of these a plus 1 and b minus 1 interval, you cannot say the function is continuous entirely from a to b. Okay, you can just take function like 1 over x for simplicity, right? So this function is continuous on, if I take this as 0 and this as 1, this function is continuous on any of a plus 1 over n and b minus 1 over n. But uh, and you have a supremum on each of these things. But if you take all together from 0 to 1, you don't have a supremum. Okay, from 0 to 1, you don't have a supremum. If you even if you take like 0.0000001 to 1, or it's like 0.0001 to 0.999999, you have a supremum, because like you're just stopping at some point. At only at 1, the function is going towards infinity, right? So the function, if restricted to a plus 1 and b minus 1 is continuous and supremum exists, then supremum of f of x is not necessarily existing, right? So that's about that question. Okay. So there was some typos, and I have shared this PDF with you, but like there were some typos that makes multiple answers for certain questions. For example, for this question I was discussing earlier, there were 2 answers, right? Yeah, we had this series is convergent, as well as uh, yeah, we had the third one, series is convergent, as well as if I'm not wrong, this one was also convergent using Cauchy quantization test. And also there was another question which I was planning to discuss, but due to the time constraint, I won't be uh, from the last few ones which had two answers. I'm not sure which one. Right. So I'm fine with discussing further, but seems like most of you guys are tired and like, do you guys have anything specific to ask, or else like those who are here, anything specific to ask, or else like anything specific you have problem with? So far we have discussed. There are some interesting problems I have gathered from somewhere, and like some problems I created myself to discuss, but seems like that's too much analysis for a day. If you guys have anything specific to ask, or else like clarify, or else like it shouldn't be necessarily from here, like it can be even from some other results or theorems from analysis, or else like some specific sections or anything, we can help with that, or else like we can wind up. Okay, I'm getting something. No. Not, we can wind up. Uh, is he there? Are you there? Okay, I'm getting something. Okay, so I don't have I haven't recorded the society members recorded, so you can ask the recording from them, right? Uh, if you have anything particular, you can ask, or else like we can wind up. You can unmute and ask, or else like drop on chat. Also, if you guys really want to discuss further, I can just discuss one or two more questions. Totally fine. If you guys are willing to engage and like discuss further. Okay, so if you guys don't have any problem, we can wind up, right? Get me, yeah?
Yeah, it seems like they have don't any questions.
Right.
So
Okay.
yeah, we can wind up.
Right.
Thank you so much, Aya.
Right. Okay. Thank you.
Thank you so much, everyone.